Hello?
Hello.
All right, finally made it. Now I'm unmuted and it's
Okay.
man, that took too long.
That's all right.
Okay.
That's really weird, but anyway, let's proceed.
Yeah.
Okay,
Cool.
so proposition book 335. It's the first one for today. And it says that if two straight lines in a circle cut one another, as in this kind of picture here. Call that E. So if two straight lines cut one another, the rectangle contained by the pieces of one is equal to, as in has the same area, the rectangle contained by the pieces of the other. That is, AE times EC is equal to BE times ED. Alright, so we're going to make some constructions. The first is to find the center F. If E is the center, then it's obvious that the statement is true, right? So we will presume not, and let F be the center, and join all the things. So that means we join FE. I'm going to construct perpendiculars FG and FH to AE and ED. That is proposition 1.12. Oops.
And also because I have
So here is it's kind of a little bit small, but it'll be fine. There's G, that's meant to be perpendicular. There's H. And I'm going to join F to B and F to C. Okay, so this is like a really slick little argument. Alright. Note that GF cuts AC in half. Similarly for FH and BD. Right, and this is by an earlier proposition in this chapter, 3.3. Okay. So AG equals GC. So now basically a lot of the heavy lifting is going to be done by proposition 2.5, which was, if you remember, basically this distributive law for squaring, right? Like a plus b squared is a squared plus 2ab plus b squared. I'll just remind you what that says for this particular line AC. So 2.5 says, well, it wasn't quite stated in that way because that sort of isn't idiomatic in Euclid, but what it said instead was something like, if you take a line and you bisect it, then the product of that with that is the largest possible thing you can get among any products of parts you get by dividing the line. That is, a squared is bigger than ab if a plus b is fixed, right? So that is smaller, the product of those two segments. So then you can say, okay, if I take the midpoint, how much smaller is that times that than that times that? And the answer is expressed in terms of the difference, right? So that's proposition 2.5. So what it says in this case is that AG times I'll say it the way Euclid says it, rather than saying times. So the rectangle of or contained by AE and EC, which is not, those aren't equal parts, but that is equal to plus the square on the difference, right? So that's less than AG times GC, which is square, the rectangle on these two parts plus the square of the gap between the midpoints and the midpoint in E's, that's GE, is equal to the square on the whole thing. So it's equal to AG, I'm going to just say times. No, not. Okay. Is yeah, I struggle with this historical, but I kind of like it at the same time. Is equal to the rectangle on AG GC. All right, which is the square on GC. So let the square on GF be added to both. Okay, well, by Pythagoras, which is the end of book 1, 47. Adding the square of GF to the square on GE is the square on FE, right? The square on FE, is equal to the sum of those two squares, and that was added to the square on the rectangle on AEC. So plus the rectangle on AEC equals the square on GC plus square on FE. But by Pythagoras again, that is the square on FC. So that's proposition 1.47. But FC is a radius because F is the center. So that equals the square on the other radius, square on FB. And by the same argument, you just apply it to the other line, BD. For BD shows what? So we said that the square on FE plus the rectangle AEC equals the square on GC plus the square on FE equals a whole bunch of other stuff. And at the end we get so that shows the square on the FE plus rectangle AEC equals the square on FE, which is the same for both lines, right? Plus the rectangle on, let's say, BEED. And then subtract the square on E from both, and we get the conclusion. Yeah, I found that very satisfying.
Cool. Thanks, Dan.
All right, so I will detach.
Thank you. So 36 is the external version of the one we just did. Just move over a bit. And it takes as a starting point a point outside the circle, and you draw lines into it. And the proof is, I mean, in spirit, similar in that it's an application of a bunch of Pythagoras' theorem, right? I find this interesting because I remember, well, maybe I'm wrong, but I think when I learned these facts in school, it was through similar triangles. Maybe. Is that right? I don't know.
No, I don't remember learning these things in high school. Maybe we did, but
It's been too long. I might just be making this up because it's, but it's nice to see, using Pythagoras. So the statement is a mouthful, but it's essentially the external version of 35. So if some point is taken outside a circle, and in fact, I think the statement will take up the whole page. And two straight lines are drawn. Lines radiate from it. Use the language Euclid from it. I guess towards the circle. Right. One of them is a tangent, and one of them cuts the circle. Right. One of them, and it's raining. One of them.
Get out your umbrella.
Yeah, it would be awesome if the avatars did that. One of them, and the other touches it. There are a lot of ands in this sentence. Apologize for that. Okay, so so essentially, we just go a circle, a point, you draw a line that cuts it, and then a line that just touches it. So that's a tangent. Right, so now we're going to talk about some areas, so really of rectangles, and that's just really multiplying lengths of line segments, right? But the language that we're using, we're talking about rectangles. Then the rectangle contained by the whole straight line cutting the circle. I wish I had a diagram here, but I won't have it till the next board. Whole straight line cutting a circle. So you have the line, right, cuts the circle in two places. It's just to the farthest end of the circle. The second time it cuts the circle from the original point. So the whole straight line, this is what it means by the whole straight line, cutting the circle, and the part of it cut off outside the circle. I guess this is clear. Part of it. Part of it cut off outside the circle. I guess this is shows us the inefficiency of the English language to describe geometrical figures. And the part of it cuts off outside between the point and the circle. And the convex circumference.
Mm-hmm.
Will be equal to the square on the tangent line. That's easy to say, right? Be equal to the square on the tangent line. Okay, so I was debating whether I should write the whole thing out, but I did. I guess this is what it means to go through Euclid, right? You have to read it the way he writes it. Okay, so now the picture is actually very simple because, well, we're only gonna have a circle, a point, and a couple of lines. So that's really all we've described so far. Now we're going to draw the circle in a specific way. To start with, we're going to assume that, well, okay, this is the point outside. We're going to call this point D, right? This is the point outside the circle. I'm not going to name any points in the circle as yet. So we know that we have a tangent line, right? So there's our tangent line. And we're going to call the point of tangent CB. And we're going to have a line that cuts the circle in 2 points. So not another tangent line. We're just going to draw it from D. and cut it. We want to draw this in a way that cuts through the center. So I guess I'm starting the proof. May as well just start the proof. Right. So we're going to assume the line. Well, assume the non-tangent line cuts.
What do you mean assume?
Or passes.
This is part of the proof, or like
Well,
obviously we need to
so
prove
we
it in
have
general.
we have a point. Two cases. So we're going to do this first and do it in the general case. I think the proof of the general case doesn't work in this case. So it's really two cases, right? So for case one, assume the non-tangent line passes through the center, and the center is here. So I think in the previous proposition, there was these two parts, but it was obvious, right? The case where the thing passes through the center, it was just clear, and then you do the general case. But there's a little bit of a proof to be done for the case where f is the center, so this is the center, and we're going to draw. We're going to join these two lines, B and F, right? And of course, there's a proposition that tells us that this is a right angle. I'll refer to that a little bit later. And I guess I need to label the other point, the other 2 points, right? A, right, and then C. And then it'll tell you what the claim of the proposition is in terms of symbols. So the claim is that we take the line, the whole line, which is DA, right? The rectangle on the whole line, right? That's made by DA, and the part of it cut off outside the circle, that's DC, right? That's this part, right, outside the circle, the convex point and the convex part of the circumference. And this is equal to the square on the tangent, which is BD squared, right? So this is the claim that we were making in the previous board with all those words. That's it. Okay.
Yep.
So I'll continue the proof on the next board. So you can already see that there's probably going to be some kind of Pythagoras theorem involved because we have a square there, and that's what we're going to do. Okay, so so this is continuing the proof. So by proposition 318. FBD is a right angle. So this is the angle I already marked on this. The FBD is a right angle. And why is it a right angle? Because there's a semicircle there, right? So, not semicircle. It's a tangent line, and you draw a line from the tangent line to the center, and that meets this tangent line at the right angle. That's proposition 318. So now we have to recall proposition 2.6, and I think, Dan, you used proposition 2.5. So so this is the another one of those geometrical type propositions that can be kind of expressed in an algebraic way. So I'm going to do that and then label the lines on the diagram to make it easy to see what's going on. So recall proposition 2.6, right? So I'll just give you the algebraic form. This is really kind of weird when you first see it. I guess we commented on this when we went through this proposition before because it was kind of strange. But it is an algebraic identity that we know. We probably wouldn't write it like this, but that's just a binomial expansion, right? Really. But we're going to go back to the previous page, and I'll tell you what A and B are so that we can apply this. So, did I just detach? So
the moon hurries back up the sky.
Oh, is that what happened? Yeah, that's right. So we're gonna label some points. So the A in the algebraic expression there is just going to be the radius, right? So all of these are radii, and B is DC, right? So this is equal to B. Okay, and so now we can go back to the identity and figure out what it says about the diagram is telling us that some quantities, when multiplied together, are equal to some other quantities multiplied together. Well, and add another term, right? So let me just get it back in position. Okay, so what does this say? This says that, yeah, so I guess this proposition is a little bit longer. I guess we have to do some work to prove even just the center case, and then we have to do the general case, right? So, okay, so since, oh, hang on. So since F is center, right? So then we have BF is equal to CF is equal to AF. And that's what we labeled A in the picture. And this is probably should put in brackets. This is the radius. Okay, so these are all radii and they're all equal. I'm going to call it A. And so hence we're just going to look at the diagram and figure out what is going on. So 2A plus B is really dA, right? That's the whole line, right? You got two parts of the radius plus the B, which is the part that pokes out of the circle. So that's dA. And times B. B is dC. That's the bit that pokes out of the circle. So we've already got one side of the equation, dA times dC. And what's A plus B squared? A plus B squared is dF squared.
You forgot.
Right?
You forgot the A squared.
Oh yeah, I'm gonna shove it on the other side.
Oh sure. Yeah.
So yeah, because I'm gonna
minus signs, Kenneth.
Oh, all right. Well, I'll put it back on the side. All right. So how is this gonna? All right. So AF dF squared, right? A squared is BF squared, right?
Yes.
So there's a square on BF, and this is the tangent. Where's no, BF is
that's the radius, yeah.
That's the radius, yes, because we already have. So that's the radius. So what we got? So now we subtract the radius from both sides. We're allowed to do that, right? Now we just take away the radius from both sides, and so we have dA.
Wait. Well, I'm still going to object to the minus signs. Aren't you going to add BD squared to both sides or something? That's what I assumed you were
am I going to add BC squared to both sides? I guess with the way I did this, I just kind of... okay, we'll do it right. So, okay, let's do... What am I doing? I'm adding BD squared to both sides. All right, let's do that.
Well, I don't know, but that would make... Then you could get DF squared on the left, and what's... Wait, so I'm a bit...
Oh, yeah. You're right. So yes, let's do that. dB squared on both sides, and I assume a Pythagoras would allow us to cancel some stuff off, right? Because now we can say that. Well, where's the triangle? The triangle is so by Pythagoras, which is proposition 147. Right. What is the formula that? Well, what is the equation? Right. That's B. I guess it's dF. Right. Squared. That's the what do you call it? Hypotenuse. And then you've got BF squared. Right. And then I guess you have the dB squared. Right. So you got that, and now you can take this away from both sides and get rid of these.
Yeah.
And then you have the conclusion. So therefore, dA times dC is equal to dB squared, which is what we wanted to prove. So now remember, this is only the baby case, right? This is we assumed a very special configuration, and so now we have to do the general case, and this is going to be a similar argument but slightly more involved because we have to do some constructions. It's going to be a similar kind of argument, right? But there'll be more triangles floating around and more applications of Pythagoras' theorem. It's going to be fun when I get there. I was subtracting stuff all over the place. Okay, so this is a general case. The general case is going to be, we're still going to keep some of our labels. This is our point, external point D. We're going to draw the tangent line first because it's easy to draw. Draw that first. All right. So we had that. Now we're gonna relabel the center of the circle as being E, right? That's just what we're gonna do. And so this is the general case. This line is just going to pass through. It's not going to pass through E. It's going to pass through some other set of points, right? But we're still going to call the farthest point of intersection from DA and the closer point of intersection C. Okay, so this is kind of the diagram we had before, right? But now we can't use the same argument, so what do? So now the construction. So now the construction is that we're going to drop a perpendicular from E to AC. Okay, so we're going to do that. So we're allowed to do this. Proposition 1.12, right? Right, allows us to kind of drop perpendiculars like this. And what else do we need? We need to join some lines, right? We need to join DE together. Okay, so and then we need to join EC together. Well, just joining points together, that's okay. And we're still going to have this line here, right? And as before, because E is the center of the circle, we're still going to have this right angle here. So this is the same as before. And while we're here, I'm going to label the well, let me come back to this. Okay, so I'm going to go to the next board and keep writing the rest of the proof. Okay, so now what do? So now the first thing I'm going to say is that by proposition 3, 3.3, EF. So EF is the perpendicular we just dropped. Is that right? Where was F? Sorry. I forgot to label the F. That's why I'm confused. F. Okay. F is the point of intersection of the perpendicular from E to AD. Okay, so EF, right, cuts AC in half. Okay, we have any point in the circle meeting one of these lines through the circle at right angles, cuts it in half, and i.e. What is AF is FC. So I was about to label this on a diagram because I wanted to do this, and I guess now I can, right? AF and AC are the same, so these two are the same. They call them A, right? And again, I'm going to call DC B. So this label is the same. So you can see what we're going to do. We're gonna try to invoke some of these. We're going to invoke proposition 2.6 again, and I won't write it out again because we had it in the previous board, but by proposition 2.6, I usually do this in blue, don't I?
Let's see.
2.6. So now this is going to look kind of similar to what we had before, but I'm gonna get rid of the minus sign. So AD, so what is it? So AD, hang on, did I do DA? Well, let's be consistent, at least try to be. DA DC, right? DA times DC plus CF squared is equal to DF squared. Okay, so this is just an application of 2.6, right? DA times DC is just 2A plus B times B, and then you put in the squares.
Yeah.
But these aren't CF. CF is no longer the radius. So we have more work to do to get to where we want to be. So next,
let's see. Yeah.
Right, we're gonna do a bunch of Pythagoras. A bunch of applications of Pythagoras' theorem, and I'm just going to write out the triangles. Well, I won't write out the triangles. I'll write out the equations that come from these triangles. Equations equating sums of squares to another square. So okay, I'm going to CF squared plus EF squared is equal to CE squared. Okay, so that's looking at well, you can look at a diagram and see it's a CF. So it's a little triangle, CFE, right? Little triangle we drew is a right angle because we dropped the perpendicular. EF, right? That's a perpendicular. So we have a right angle triangle. One of the sides is A, right? I guess I'll figure out which one's A later. There's a BD squared plus BE squared is equal to ED squared. Okay, so this is the bigger triangle. Well, this is the this is the triangle we had before, right? This is the triangle that's constructed from the tangent line, and then one of them is a radius, BE is the radius, and then you have a hypotenuse now, which is not the hypotenuse we want, but okay, we have it in there. And then we have another triangle, right angle triangle, the third one, EF squared plus DF squared is equal to ED squared. So ED is the is a side in two different right angle triangles, and so we this is just the other one. It's like the slightly smaller one by the picture. Okay, so now I'm going to have to add the right things to the right side to cancel stuff off. See if I can do it. So I did this with minus signs, but Dan objected, so I'm going to try and do it without the minus. And if I start messing up, well, you can help me. All right, so DC, I'm going to start there, and we want like BD on the other side, right? So we probably have to add a whole bunch of stuff to both sides. So EF and then cancel stuff off, right? So I'm going to add BD square to both sides because the statement we want is that this thing is equal to this thing. So right, so we're adding both sides, and we've got CF squared. So we probably should add EF to both sides. All right, so I'm going to track this colors. EF to both sides. Okay, so you got CF, EFCE, right, squared.
Sorry, could you just walk your character forward slightly?
Am I?
No, the orb cam keeps like doing some weird thing. It's a bug, but this should fix it. Yeah, thanks.
Okay, cool. Awesome. Okay, where was I? So I added EF to both sides. So so I have DF and EF. All right, we're getting good, right? So now let's add ED to both sides, and I think we're good, right?
Yeah.
Okay, so now we can. I shouldn't have colored them. Now this is now.
It's fine. It's Christmas. It's Christmas.
Yeah. Oh yeah. I got me some Christmas colors too, right? Awesome. So CFEF, right, is CE. Where's CE?
CE. Yeah. So that'll give you CF plus EF. You want EF?
No, CE is a radius. CE is a radius. So we can kill this guy some other way, right? So this guy is secretly a radius, right? Mm-hmm. Who else is secretly a radius? BE is secretly a radius.
Yeah.
Yeah, I'm going to circle all the radiuses. So this guy's a radius. This guy's a radius. And I think that's it. There are only two radii floating around, right? So what do we do? So BE, CE. I still don't see it. All right. So ED. So CF EF is CE squared, right? So that's really BE squared, right? So this thing is really secretly BE squared, and BE squared plus ED squared is equal to ED squared.
BD squared.
Sorry, BD squared.
Yeah.
Oh yeah. So BE plus BD is ED squared. So I really secretly have two lots of BD squared here. So on the right hand side, I'm getting that DF squared plus EF squared is going to be ED squared. So now we're good. Yeah. Okay.
Yeah.
So this is ED squared. And then, sorry, this is super confusing. It probably doesn't have to be BE and BD. These are ED squared, right? So now we have two lots of ED squared. We get rid of them, and we have our conclusion, which is that DA times DC is BD squared.
Very good.
Oh, yeah, so this is a bit more involved than the previous one.
Yeah, I agree.
Yeah, this is meant to be, right? I think the external code was more involved, even if you proved it without Pythagoras.
Yeah.
All right, so the last proposition of book 3, Dan.
Yeah, very good. Okay, where's the orb?
Yeah.
Here we go. I think
I
may only need one board. Let me just check before I...
Oh, wow.
It's pretty short.
Oh yeah, it's only a page.
Yeah, I reckon.
It's a bit wordy, but probably not too bad.
Yeah, I
Cool.
reckon we can get it on here.
Nice.
Okay. Proposition 3.37. Okay. So, if a point outside a circle is taken, it's just the converse of proposition 36. And a line that meets it and the rectangle of the whole line that meets it from the other side, so to speak, of the circle to where it starts times the part that's sticking out, as Kenneth was just describing. I'll just say of the previous proposition, to repeat it.
Nice.
Repeat it when I've got the diagram. Is equal to the square of the line that meets it. Of the line that touches it, rather. Line that meets it, sorry. Then the latter line touches. Alright, so just to draw the diagram. So we have a situation, here's the point outside, and we have two straight lines, so DCA. And then we have another line DB, which we don't know it touches, right? I'm going to draw it as though it touches, but we're taking two lines that meet the circle, and one of them, DB, potentially touches, and the other one we sort of, by construction, know does not touch. So hence we give the name C to where it meets the circle. And what we suppose is that DA times DC, that's the rectangle, is equal to the square of DB. And then we're going to prove that DB actually touches rather than sort of properly meets. Okay, so let DE be drawn touching ABC. So that we did earlier on in this book. So that looks like this. So this is actually genuinely touching. And let F be the center. And join all the things. And DF. Alright. So, by what we just did, we know something about 36. We have that DC times DA equals DE squared. By hypothesis, this also equals, because DCDA is assumed equal to DB squared. So we have DE squared is equal to DB squared, hence DB equals DA. because we believe in square roots or something, but just by contradiction, right? If they were different, one would be smaller. Draw the diagram. Okay, so dB equals dE, and of course FB equals FE, because they're both radii. So the two straight lines DE FE are equal to the straight lines DB FB, and of course the bases are equal because the base is shared. So by whatever it is, proposition 1.8, the angles must be equal. So DEF equals DBF. But DEF is a right angle, because we know that if a line is a right angle, because we know that if a line touches, then it makes a right angle with the radius. And that's if and only if. So we're done, right?
Nice.
Yeah.
Well, it's nice that the converse is relatively straightforward, using the forward direction and this construction.
Yeah, I like it. So
Nice.
it's dBF, hence by the same proposition. Well, I guess there's 3.16 and 3.16 corollary is the consequence. Yeah, I like how Euclid never ever says like if and only if or something, right? That's always like two separate propositions.
Yeah.
dBF hence by the same proposition. dB touches.
Yeah, I guess if kids grew up studying this, they would probably understand if and only if a lot better. They'd probably run into creating these proofs that confuse the forward and backwards directions all over the place, right? Separating them means that they occupy different. They're different, right? They're different propositions.
Yeah, I agree. That's interesting.
Yeah.
All right.
Like a lot of modern ways of doing it, like the forward and backwards directions are almost the same proof, and you think, well, don't I? Yeah, but anyway, sorry, I interrupted you. This is the last proposition.
That's right. Yeah, so we are finished with book 3. Nice.
Awesome.
Yeah, as I mentioned on the Discord, actually, although there's many more books, at least books 4 through 9 don't take up twice as much as the books we've done so far. So it's we're closer to finishing at least my version of the PDF, which goes up to book 9 than it might seem. So.
Oh, cool, nice. Well, yeah, I'll stick with this. This has been fun. But yeah, we'll take a break, I guess, as you said, and we'll come back sometime 2024.
Yeah, thanks, Kenneth. It's been fun.
Cool. Yeah, enjoy your holidays, man.
Yeah, Merry Christmas and Happy New Year.
Merry Christmas.
Okay,
You too.
see you, mate.
Bye bye.